Hey, how's everyone doing today? Recently in class, we've been studying how to solve systems of linear equations algebraically. Today, what we're going to look at are some special types of systems of linear equations. So, when we solve a system of equations, there are really only three possible solutions that we can get. One is one unique solution. So one unique solution would mean one ordered pair that is a solution to both of the equations in the system. The second one would be no solutions. And we've discussed this in the past, but we'll review this again when a system of equations will have no solutions. And then finally, we could have an infinite number of solutions. So infinite number of solutions. So instead of just having one ordered pair, one unique ordered pair that satisfies both equations, here an infinite number of ordered pairs will satisfy both equations. All right, so one unique solution is a single solution that can be listed as an ordered pair. If we think about a system of equations graphically, so two linear equations graphically, if they intersect at exactly one point, that's where that system of equations is going to have one unique solution. Now, we could also have no solutions like we discussed above. So on a graph, the lines will be parallel, which means that the lines will never intersect. So graphically, if we see a pair of parallel lines that never cross, that means that system of equations has no solutions. So if we analyze the equations, what we're going to notice is that they should have the same slope, but different y-intercepts. So that's going to make them parallel. Now, when we're solving algebraically, the variables will zero out, and we're going to end up with a false statement. And again, I'm going to illustrate this for you later on. So graphically, we've seen a pair of parallel lines, and now what we're going to talk about is, well, what happens if we're solving algebraically and the variables zero out and we're left with a false statement? What is that going to look like? Well, that's going to tell us that there's no solution. And again, we'll go through and do an example of that in just a couple minutes. And then finally, as we mentioned above, we could have an infinite number of solutions. Okay, so on the graph, the lines will be overlapping. Okay, and you may hear the term coincident. So coincident lines. So again, if we were to analyze the equations in a system where there's an infinite number of solutions, we would have the same slopes and the same y-intercept. So in essence, they're the exact same equation. So using substitution or elimination, so algebraic approaches to solving that system, the variables will zero out, and we'll end up with a true statement. So again, when we're solving a system that has no solutions or an infinite number of solutions algebraically, if we work them down far enough, we'll notice that the variables are going to zero out. If we get a false statement, then that means that the system is going to have no solutions. If we get a true statement, that means that the system is going to have an infinite number of solutions. And if we work it out algebraically and we just get an ordered pair, or actually we just get a solution for one of the variables, that means that we're going to have one unique solution. So let's go ahead and take a look at some examples. Okay, so again, like I had mentioned before, let's take a look at a couple of examples here. The first one reads, solve the following systems of equations by graphing. So we're going to do that quickly. So the first line is y equals 2x minus 4. it's in slope-intercept form. So what I'm going to do is I'm going to plot the y-intercept, and then I'm going to follow the slope to generate additional points on the graph. So the y-intercept is -4, so I'll plot that over here on my graph. The slope of the line is +2, so from the y-intercept we're going to go up 2 units, and then 2 units rather, and then to the right 1, up 2 and to the right 1. We can go down 2 into the left 1, and down 2 into the left 1. Normally, I connect the dots with a straight edge, and you should do that. You should get in the habit of doing that as well. The next line is in standard form, so what I'm going to do is use the cover-up method and find the x and the y intercepts of this graph and graph it that way. So I'm going to cover up the term that contains y, and we're left with 4x equals 8. So if we divide both sides by 4, we're going to get x equals 2. So the x-intercept is 2, which it appears that the line that we drew previously also has an x-intercept of 2. Now we're going to find the y-intercept, so I'm going to cover up the term that contains x, and that's going to leave us with the equation -2y equals 8. So we'll divide both sides by -2, and we're going to get y equals -4, which means that the y-intercept of this graph is -4. So if we were to connect those dots, you would see that the line that I draw in is going to be overlapping the other line. So in this situation, this system of equations has an infinite number of solutions. And if we think about this graphically, every single point that we select that's on the blue line would also appear on the red line. So every ordered pair that works in this top equation is going to work as a solution in the bottom equation. Now, if we go through this quickly algebraically, I'll use the substitution method to solve this system. So what I'm going to do is I'm going to replace y in the second equation with 2x minus 4. So let's go ahead and do that. So we're going to get 4x minus 2 times 2x minus 4 equals 8. So we'll distribute this -2 through the parentheses. That's going to give us 4x minus 4x plus 8 equals 8. And as I described on the first page of the notes, here the variables are going to zero out. 4x minus 4x is 0, which leaves us with 8 equals 8. And again, when the variables zero out and we're left with a true statement, 8 does equal 8. This is true. Again, that's telling us that this system has an infinite number of solutions. So now what we're going to do is move on and take a look at a couple more examples. Okay, 2 more examples to go. Number 2 reads, solve the following system of equations using the substitution method. Okay, so we'll try that out. Here, I think the best substitution to make, the second equation is solved for y in terms of x. So I'm going to replace y in the top equation with 2x plus 5. So we're going to get 3 times the quantity 2x plus 5 minus 6x equals 12. Okay, so again, I'm going to distribute. So 3 times 2x is 6x. 3 times 5 is positive 15. Minus 6x equals 12. So we're going to combine like terms here. 6x minus 6x is 0. And 0 plus 15 is 15. So we're left with this statement here, 15 equals 12. And if we take a look, 15 clearly does not equal 12. This is a false statement. And what that's telling us is that these two lines are going to be parallel if we graph them, and that this system of equations has no solutions. Now what we can do is up here, I can convert the top equation into slope-intercept form. And what should happen is we convert that into slope-intercept form. The two equations, so this one, y equals 2x plus 5, and this one here, should have the same slope but different y-intercept. So to solve for y, I'm going to add 6x to both sides. we'll get 3y equals 6x plus 12. And now we'll divide both sides by 3. And we're going to get y equals 2x plus 4. So again, if we analyze these two equations, y equals 2x plus 5 and y equals 2x plus 4, they have the same slopes, 2, but different y-intercepts, which means that those two lines are parallel. The system of equations has no solutions. All right, so we're going to do example number 3. This one reads, solve the following system of equations using the elimination method. So what I'm going to do here, the top equation is already written in standard form. I'm going to rewrite the bottom equation in standard form. So let's rewrite the top one, 9x minus 5y equals 8. And then I'll bring the 9x over on the bottom equation, so 9x minus 5y equals 12. So if we look here, when we use the elimination method, really what we want is the coefficients of one of the variables to be the same number but with opposite signs. So what I'll do here is I'll multiply this bottom equation by -1. Use a different color for that. So again, I'm going to rewrite the top equation, 9x minus 5y equals 8. Bottom equation, we get -9x plus 5y equals -12. All right, so now we can add these two equations together. 9x plus -9x is 0. -5y plus +5y is also 0. So we get 0 equals, and then 8 plus -12 is -4. So again, very similar to the previous example. 0 does not equal -4, that's a false statement. So this system also has no solutions. And what I would encourage you to do is go ahead to Desmos, graph these two equations, so graph the lines that represent these two equations, and what you're going to see is that those two lines are indeed parallel. All right, so what you're going to do now is go ahead and try some examples on your own. I've posted an answer key to Google Classroom for you to check out. As always, I hope this video was helpful, and we'll see you in the next one.